I might just start. So, good afternoon to everyone. My name is Michael O'Donovan. I'm the current chair of the electrical division in Engineers Ireland. I'm delighted to welcome you today to the webinar hosted by the electrical division with the support from the electronic and computing division. Before we begin, I'd like to thank a few people supporting today's session. Thanks to Kate from Sector Support. She's managing all the Zoom logistics and the promotion. Thanks to Ed, who's a member of our committee, for monitoring the session and bringing forward your questions, and to Charles for his support in organising this event, and we'll close the event. Just a reminder to look out for our AGM in early May. We'd be delighted to welcome new members. The electrical division is a friendly and engaging community, and we'd love to have you involved. I suppose I'd like to promote an event that's coming up. You can join us on Thursday, the 16th of April, for an in-person event. It's a timely seminar exploring how engineering can help close Ireland's climate gap and meet its 2030 targets. Hosted by the Energy, Environment and Climate Division, this event brings together leading experts to discuss real solutions for low carbon future. And don't miss your opportunity to be part of the conversation. So you'll see that link. It'll be pasted so that you can follow us. I suppose today's talk is submarine cable technology, from Telegraph to what the future holds and how do we secure them. It's now my pleasure to introduce our speaker, Derek Cassidy. We go back a long way. Derek is a chartered engineer with only over 30 years experience in telecommunications, specializing in submarine networks and optical engineering. He's the chair of the Irish Communication Research Group and a technical lead for the Valencia Transatlantic Cable Foundation World Heritage Bids. I'm sure he'll mention that. He's also past chair of the IT. You remember Happy Days in Cork with Derek and Dr. Chris Bruce, where Derek was always happy to volunteer to speak on a communication topic. So please join me in welcoming Derek. So Derek, I hand it over to you there.
Yep. Thank you very much for joining. Right, this is going to be a brief overview of the telecommunication network via submarine systems, going back from the early days of the telegraph all the way up to what's happening today. So basically, this is how it started. 1842 really started the actual telegraph, the very first submarine cable. But the actual very first submarine cable was actually laid in 1839 in India by an Irish doctor who discovered that gutta percha is an insulator that actually works perfectly. Submarine cables themselves actually became a possibility when another Dublin cafe owner, Bewley, which Bewleys are still around, actually developed a technique to extrude gutta percha over copper core. So basically what that enabled the development of submarine cables. So in 1850, the very first submarine cable was laid, and it failed after one day. This is just a list of the actual people who are involved. Obviously, you'll be able to read it when you get a copy of the list, a copy of the actual presentation itself. So basically, from 1836 to 1866, telegraph networks were either terrestrial or they were short haul submarine systems up to 150 kilometers. That's all they could actually do. Here I actually talk about the Morse code. Everyone knows about Morse code, but everyone thinks that Morse code was invented by Samuel Morse and is still used today, which it was. But in 1865, which last year was the 150th anniversary of the ITUT, it also coincides, the fact is, in 1865, they actually decided to use a continental Morse code, which is exactly like the ITU one. It was actually developed by a German telegraph engineer called Gerk in 1845. And in 1860, he started to use it in Germany. And in 1865, with the establishment of the Telegraph Union, they actually took it on board. So that's the actual Morse code that we use today. It's not the Samuel Morse code, it's the Gerk Morse code, or people in the industry call it the Gerk Hamburg code, basically because it was developed in Hamburg in Germany. Another Morse code or type of system was the actual 5-needle system that was used on the railways in the UK, Wheatstone and Cook and they actually have the patent for telegraph from 1836. And they developed the 5 needle system, which basically worked along the railway network. And then over on the very right, you'll actually see a telegraph printout of what looks like noise. It's actually the way telegraph engineers would actually see the electrical current. They can actually identify the dots and the dashes. Didn't actually most people think that it actually came in as a sounder, which it did on a dot and a dash, as in a long pulse and a short pulse. But when ticker tape was invented in the 1850s, it came out something like this sometimes, or it actually came out with the dots and dashes. It depends on who actually made the actual system itself. But telegraph engineers and people who actually read it could actually understand exactly what was actually being sent. And also another thing as well, and it was well known in when the Titanic was actually struck by the iceberg. Telegraph engineers could actually understand who was actually sending a telegraph message by the actual pulses. So basically, you could have 12 people on 12 different keys on 12 different cables, and they could actually know who was actually sending the message by understanding the pulse. There's a copy of the 1850 Dover to Calais cable. The Dover to Calais cable was laid in 1850. Unfortunately, the same day, a French fisherman thought it was seaweed when he pulled up his anchor, and he cut it. So that was the first ever recorded damage to a submarine cable on the exact same day the submarine cable was laid. So in 1851, the Brett brothers, who actually laid the 1851, came up with a new design which was armored, and they laid that across the same stretch of water again. And that cable actually lasted 37 years. Or 35 years, but the main reason why was because of the armoring. The ability for the armor to take shocks of anchors and obviously the fishing people themselves. The fact is that they could understand that if they did pull her up, it was a cable, and they wouldn't actually go near it. This is just an actual picture or a description of how the cable was made. The very top picture, the core is actually coming in, and it's actually covered in the gutta percha. And over to the right, it actually shows you how it's done. And then over to the left, it shows you how the wiring is actually wrapped around the cable itself. So basically, it's copper core into the gutta percha, and then it's wrapped around with the wire armoring. That actual design is technically something like that is still used today. So basically, submarine cables are actually wrapped in actually go through an system where the PTFE is extruded onto the fiber itself, but the actual fiber itself is in a tube, and the PTFE is actually extruded onto the system itself. So the same method is still being used, and so is the wiring. So basically, these are things that go back over 150 years that are still used in the industry today because nobody can come up with a better way. This is the telegraph map of around 1853. It shows that an awful lot of the UK is covered in telegraph systems. And then you have 2 main cables going over to Ireland, and then the cables go down as far as Killarney, Cork, Galway. They don't really go to Sligo or Mayo because basically they're not actual areas where the population is big. So basically, these lines here, the telegraph lines in Ireland, all follow the railway lines, but they only go to where the population is big, because obviously that's where it actually costs money to actually build an actual system. Therefore, they have to get the money back. So the only way they can do that is to go to major towns. So basically, here we have submarine cables actually wrapped in the arming. Over to the left, you have the 1857 cable. You notice the 1857 cable has very thin arming compared to the ones on the right. That actual arming was made of iron, while all the rest of them are made of steel. That arming on the 1857 cable was very weak because of the tensile strength. And now you can actually still pick up the 1857 cable from the seabed, but the arming iron is now gone because the microbes in the actual deep ocean sea actually basically devour it. So all you're left is with an example of, you're left with that, the 1850. So you're left with a copper core covered in gutta percha. But the gutta percha is no longer black; it's now brown because of the iron, which is actually rusted into the actual system itself, the cable itself. Now here we have different designs of submarine cable and transmission systems that actually enable the actual transmission. So basically, you went from the single core to the 4-core, and then they decided that the 7-stranded core was better than the single core, and then they came up with the 7-leaf system, and which is a bigger core, but it's all based on the film effect. The film effect is still used in coax today. So, your Virgin Media, for instance, your transmission of your TV signals are actually not transmitted in the core; they're actually transmitted on the outside of the film. Right? It's called the actual film effect. So basically, the cross sectional area, or the not the cross section area, the actual coverage of the actual copper itself. Basically, the more copper wires you have, the more face or face covering, or fill, or the outer the actual face effect allows more transmission of actual signal. So radio engineers and telecom engineers will have a good idea what I'm talking about. The William Thomson the mirror galvanometer that was invented in 1858 by William Thomson, which is now Baron Kelvin, was the only instrument that actually pick up low voltages. That's how the 1865 and 1866 cable worked. And all cables up until then, before the ticker tape, even though the printing press came out in 1855, it wasn't actually used on submarine cables until the 1870s. And then you had the Emile Bardot telegraph multiplexing system, which actually in 1874 allowed the 4 or even 5 telegraph operators to actually work on the same submarine cable at the same time. Therefore, instead of one telegraph signal going over, by 1874, you can actually have 5. The galvanometer you see there, the one on the right, is an example I have. It actually comes from the 1860s, and it was actually used in the cable that wired the world that was made by RTE 2 years ago. So basically, that actually got an Oscar because it was in every single scene that was seen. He was actually in it, because I actually provided most of the equipment for it anyway. But on the right or the left is an example of Thomson's galvanometer that actually picked up the very low voltages, because basically they couldn't pick up anything, but they noticed that the mirror itself would move slightly when there's an electrical current, and it would move left or right depending on whether it was negative or positive. And that's how they could actually read it. So basically, the 1866 transatlantic cable, which actually is the one which Valencia is very proud to basically promote for the World Heritage Bid, opened up the world to long distance communication. So basically, the longest submarine cable before that was 150, 160 kilometers. Now we had a 3,000 kilometer cable that actually worked. But it also opened up the international markets. An awful lot of people think the international markets are actually down there for years. They weren't. It was because of the 1866 cable that London and New York started to communicate within minutes. Instead of 4 or 5 weeks of knowing stocks and shares, they could actually do it in minutes. And that's actually started the actual stock market. And by 1870, London was now the center of the system. On the left, or the right, you had the SS Great Eastern. That was the one that actually laid the 1865 and 1866 cable. The 1865 cable actually failed 600 kilometers off the coast of Newfoundland, and in 1866, under Halpin, which was a Wicklow man, decided to go back out again and actually picked it up and actually relayed the 1865 from there back into Hearts Content in Canada. And within 2 months, they actually had laid 2 transatlantic telephone cables or telegraph cables. Here you have different multiplexers and all that, which allowed for extra traffic to actually go across. telegraph cables, and even you had telegraph cables actually bidirectional. So basically, you could transmit and receive at the same time. So basically, these systems, the multiplexing, actually evolved into what we have radio today, and then evolved into optics. So basically, radio took all these multiplexing techniques and actually used them to allow for the transmission of radio systems around the world. And then optics uses the multiplexing techniques, which they take from radio, which took from the telegraph. So basically, anything that was invented around the telegraph actually had an extra effect onto future comms. Here's just a makeup of an actual telegraph cable, and then here's the type of the material that's used in it. Like the conductor copper core is 1,000 years old. The insulator Gutta Percha 1843, but it was Bewley in 1848 that actually discovered it actually be used for an insulator over copper core itself by the extrusion method. Basically, Bewley is one of the main people involved in the development of the submarine cable, basically, because without Bewley and his system, we wouldn't have submarine cables today. So basically, there's a description of some of the maps that actually related to the submarine cables. So over on the very right-hand side, you have a map from 1938, which shows multiple submarine cables leaving Ireland. You notice that there's only 4 parts. Now, there was loads more, but a lot of telegraph cables by 1938 had actually ceased to operate. So, and the cable stations closed. But Waterville, Valentia, Blackwater, Newcastle, and Howth were still the main submarine cable stations in Ireland at the time. On the east coast, they connected to the UK, and on the west coast, they connected to the US and Canada. And the middle is the cables that actually leave Valentia and Waterville. Valentia was 1868 was actually built, but Valentia was operable from 1857. Waterville, I think, was 1884, and then Ballinskelligs was 1873 to 1922. Waterville and Valentia both closed in 1966. Over on the top right or top left is a charted map of the submarine cables that actually leave Ireland going to the States and to Canada, and that is from the UKHO. It's one of the handwritten maps which they had, which I actually got a copy of. And then on the bottom left is a 1901 telegraph map of the world, and you notice right in the middle is Ireland. Basically, in 1901, Britain also had a thing called the Red Line. So basically, the Red Line went from London all the way around the globe and back to London again. And it only went through British territory. So it went through Canada, went through Australia, up through India, then along the sea into the Jib, and then up to the UK. But at the center of the Red Line was the only submarine cable station which was not owned by Great Britain. It was actually owned by the Anglo-American Telegraph Company. But because it was instrumental in all the telegraph cables going to Canada, basically it was the only non-UK owned submarine cable station that was on the Red Line. But because Valentia and Ireland were still part of Great Britain at the time, it was allowed to actually happen. But any other cable station around the globe had to be owned by the UK. Here's another bigger map of the actual system itself. So basically, submarine cables, telegraph cables, were not only used for the transmission of telegraph signals. They're also used for loop cables. A loop cable is an old telegraph cable that has been taken out of service, and then they realized that if you actually put electrical power across it again, but kept it constant, by any metal object going over that cable, it would induce an electrical current on it. Therefore, the impedance would either increase or decrease. And by calculating the impedance, they can actually calculate the distance to where that actual disturbance was. Over to the left, their loop cables are actually protected naval bases in Scotland in World War One and World War Two. They were old telegraph cables which they relayed, and in the middle is the old 1862 Wexford to Wales telegraph cable. It's the longest loop cable in the world. It actually goes 93 kilometers. That cable went out of service, but in World War One, the British Navy decided to put it into service again, and they found that they can actually detect German submarines actually going over it, and even now German ships didn't, but only the subs. That's how they could actually track them. Was by this cable. That cable technically is still there, but it's damaged. It's not operational anymore, but it's still in the water. And then you have the SOSUS system, which is no longer operational, but the SOSUS system is the NATO system that they use between Greenland and Scotland to detect Russian subs. Now they have a new system which is all optical, but this was actually coax and telegraph systems, and it actually worked fairly, very well. An awful lot of colleagues in the Irish Communication Research Group tell me on the west of Ireland that they know the system no longer works because every now and then a transponder either floats and comes ashore in Spittle, Galway or Mayo. And they know if they pick it up, the cable's been damaged or something like that, but they do know there is a new system there. Then we go into the evolution of coaxial telephone systems. The very first transatlantic coaxial system was 1956, and that was TAT1. TAT1 was actually two submarine cables, which I'll go on to now in a minute. It had 36 or 36 channels one way. So in other words, if you spoke from America to the UK, you were speaking on the North cable. And then for you to listen to the person speaking from the UK to the US, the voice is coming over in the South cable. Coax is only transmissible, it can only transmit signal in one way because it's unbalanced, right? It needs to be balanced to be able to be a bidirectional cable. So basically, coax itself uses the outer shield, which creates the induction and the capacitance to conduct the actual signal itself and reduce the resistance to 75 ohms. It uses that shielding as the earth as well. Old telegraph cables used the armoring, and they also used the actual seawater itself as the earth. But in a coax cable, it's the actual shielding that's the earth. But before that, Heathside in 1880s came up with the idea of a loaded cable, and the very first loaded cable was developed in 1924. And a loaded cable is a telegraph cable with wiring wrapped around the actual core itself, which creates an increased capacitance in the cable, which allows more traffic to be sent quicker. But it was the patent in 1931 and the development, or the very first coax cable that went in 1936 in Australia, was then followed by a few more coax cables. But obviously TAT1, which you know is the most famous one, which actually went in 1956. But again, 1956, that cable actually was two cables. So it could actually only transmit one way. TAT7 was the last one. So TAT1 had 36 channels. TAT7 had 10,500 voice channels. That was the development of the multiplexing techniques and amplifiers that are actually on the systems. Every year, the evolution allowed them to increase the actual transmission of signals and increase the actual voice channels and allow more multiplexing and TDM of frequencies. So therefore, your frequency spectrum actually increased quite a lot on coax systems. Then we have the famous one. In 1947, the Irish Post and Telegraphs actually laid two coax cables over to the UK. But the smart engineers in the Department of Post and Telegraphs decided to put down an external earth, which created a balanced coax system. Now, balanced coax system is a 120 ohm system, and it's actually still used in telecoms today. It's called a 120 ohm frame. For instance, if you go into a telecom room where you have two negatives, two positives, or two transmits and two receives, and an earth. So basically, what it is That was a bidirectional, 56 channels on each cable. But by having a bidirectional cable, because there's now balance, it could actually have 112. It was the world's first ever system that actually came into op, op, operation. It was 1947, and it was 9 years before TAT1. But TAT1 couldn't employ this system because it couldn't actually develop the earth long enough. Actually, just go back to this slide and show you another cable. BTT1, which was the development of the optical submarine cables, was the second submarine cable optical ever laid in the world, and was between Ireland and the UK. The one on the right there is a sample of the 1947 cable. Then we come across to the optical. We have TAT8. TAT8 that was developed in 1988 only had 240 megabits, so two 240 megabit channels. Nowadays, submarine cables can carry up to 300 plus terabits, right? So the very first submarine cable ever laid in the world was actually laid between the UK and Belgium. It was called UK-Belgium 5 and had three 240 megabit channels. The next submarine cable laid was actually BTT1, laid in 1988. It wasn't two, it was actually six 140 meg channels, which actually was the highest capacity submarine cable network laid. Right, so far, even though it was the second one, it was the highest capacity because TAT1, which is the one over the left, was laid a couple of months later, and that only had 240 megs. By two of them, that's 480 megs, where BTT1 had the capacity was higher. And even UK-Belgium 5, which is the first optical cable, actually had lower capacity between Britain and Europe than it had between Britain and Ireland. Even thinking the fact is that Ireland at that stage only had 3 million people, and not many telephones were in the country. But yet, the capacity on that cable was higher than going to Europe. So basically, optical fiber submarine cable technology opened the door to next generation communication, and basically allowed the development of future evolutionary techniques to take place. TAT8 was followed by TAT 9, 10, 11, 12, 13, and 14. 14 was the last of the TAT cables, and it was laid in 2001. Actually, TAT 14, it was laid in 2001, was taken out of service in 2014. Didn't last very long. Even though they say submarine cables have a generation lifespan of 25 years, that's nonsense. Submarine cables, optical submarine cables, can have a lifespan of up to 80 to 100 years. The only thing that's stopping the lifespan of a submarine cable is two things: the capacity, which is limited to the Shannon limit. So basically, signal to noise ratio on an optical cable depends on the actual capacity going across it, and also the actual technology that actually goes into the submarine cable. It's not the glass. Even though glass is actually being developed now to very low losses, the glass on BTT1 can still be used today to transmit terabits. It's the technology behind it that actually changed, that actually moved away from the cable for other cables to take place. So basically, there is cables out there that are actually now running in nearly 30 years. So they are over their lifespan of 25 years already. Like two of the BT cables, which I personally responsible, ESA 1 and 2, are operational since 1999. Both of them carry terabits. Both of them are still operational. Both of them are fine. There's no issues whatsoever with the technology because they're made of a thing called pure silica glass, which is very low loss glass, which is only matched by the ITU-T reference of G654, which is the actual glass that's used in submarine cable systems today. So basically, even in 1999, they actually had the capability and the glass to actually create long-lasting submarine cable systems. Then we go into the TAD 8 again. TAD 8 came up with a very brand new design. It actually had a thing right here in the middle called a cable vault. So that cable vault is actually two arming wires that are actually wrapped around the actual fiber optic package. What they do is when the actual cable is hit, they tighten so tight that they actually create two cylindrical wires, right? So like wire tubes. They can't compress any further. And what they do is they create a smaller cylinder which protects the optical glass, right? Also, TAT1 didn't have amplifiers that had repeaters on it. The repeaters they had optical, electrical, optical regeneration on them. So basically, every single repeater actually changed it to an electrical signal and reamplified it again, and then sent it back out as an optical signal. But it also had the capability that if one transmitter failed, they could switch to another one. Also, on the branching units, because there's a branching unit going to Britain and a branching unit going to France, they could actually have, uh, even though it was a two fiber system, the branching units themselves had two fibers themselves. So basically, one fiber pair failed, they could actually switch over to a second pair on the branching unit. So basically, it had fiber redundancy and transmitter redundancy on the system as well. And then over to the right, you actually see a sketch of the actual makeup of the fibers. There is only 4 fibers on it. Now, unrepeated submarine cables can have up to 196 fibers, if not more. The only problem with a 196 fiber unrepeated cable is if it's across the Irish Sea, a 24 fiber cable takes roughly 24 hours to repair. Well, not repair, just put one joint onto it. You need 2 of them for a repair. A 196 could take up to 4 days. I've never seen 4 very clear days on the Irish Sea where a boat can actually sit and basically repair a cable. So the problem is that the more fibers you put into a submarine cable, the more issues you have with the actual repairing of that cable, the longer it's going to take. The bottom one is a sample of TAD 8. That is actually the size of, I actually have a sample over here myself. That is actually only about 1.5 centimeters diameter. So basically, it's very small, right? And then the armoring itself goes around it. So the actual submarine cable, TAD 8, was a small cable. So basically, you have 2 pictures here of 2 submarine cables, right? The one on the left is the one with the vault, which is a very great design. It's patented by Subcom. It's an American company that actually, all my cables have it. It actually protects the actual fibers. Other cable designs actually just had the armoring, then I had a covering for the fibers. The problem is that when a trawl door, for instance, from fishing hits a submarine cable with a vault on it, the vault itself, as I already said, actually creates 2 cylindrical pipes, which are so tight and so strong, they actually protect the fibers unless you have really critical damage that actually an anchor or something will cut the cable. But on the right, you have a cable that if it is hit by a trawl door, you have a high tendency for the cable, the armoring itself, to squash and actually cause the actual fibers themselves to break. So here's another few examples of some 2 submarine cables going across the Irish Sea. Top 2 are 2 other operators that actually have it. They have the tube method, while down the bottom right are my cables, and they have the vaulted method, right? But the one on the right actually is a tube method. It's the cable we use. We don't have much. We do have traffic on it, but that not much. These are other cables which you have an awful lot of traffic on it because we trust the actual vaulted method. It's the cable themselves have very rarely been damaged. They've been hit by trawl doors, they've been hit by beam trawlers, and they're still fine. No problem at all. The only damage that is ever done to them are anchors. You've got a 10-ton, 20-ton, depends on how big the anchor is. Dropping on the cable is fine, but when it picks up the cable, and my anchor damage is actually down to the cable, the anchor picking up the cable, sometimes out of 2.5 meters of silt and sand and mud because it's buried. It's bringing all that tensile strength, the compression strength and everything else coming up. and the cable itself can only hold so much, and then all of a sudden the tensile strength just breaks and the cable snaps. And then you have here power cables. We also have submarine power cables. For instance, the EWI cable, which was laid in 2011 between Wales and Ireland, and now the Celtic in interconnector, which is being deployed. You notice that has an optical cable in it. I helped design the EMIC cable, and I insisted an optical cable go into it. Not all submarine power cables have optical cables, but all the ones Airgrid are putting in do have optical cables in them because they're ideal for communication and they're ideal for communicating with the far ends. So you don't have to send another cable over for telemetry. You can actually embed it into your whole system itself. And it's a great idea to actually even to sell traffic on that optical cable, because that optical cable now has the protection of the actual whole package that surrounds the actual power cable, which is very strong. Now you have other types of submarine cables that are used around the globe today. On the left, you'll see the tube method, and on the right, you'll see the vaulted method. Loads of different makers, even though Subcom had patent on this, they actually allow other makers to make it. And then other makers will actually do this as well. It depends on which system you go for. It depends on whether it's going to be deep sea, whether it's going to be a repeated system between the UK and Ireland, or UK, France, or a local cross river or very short distance. You probably use this. But if it's going an oceanic cable, you probably use one of these. And these are the ones we use. I'll be fair, these cost a bit more, but they last not longer. Then you have the milestone was reached in 2018. 2018, the very first hyperscale cable came into operation. It was a cable that was not designed for commercial operations. In other words, it wasn't open to telecom companies to actually send traffic on. But saying that, telecom operators are the only companies up until the last 2 years that could actually lay these submarine cables, because telecom operators had the license to do it. The likes of Google and Amazon and Meta and all didn't have a license. Therefore, they had to go to these operators to do it. And in doing so, if they had, say, 8 fiber pairs, which is 16 fibers, or probably 8 fibers in the submarine cable, the telecom operator might get a pair to actually allow him to use that cable. But the cable itself was still a hyperscaler cable, which is the data centers. Basically, as we look at them, here's an example of some hyperscaler cables. I haven't mentioned which hyperscale project it is, I don't really want to. But all these can actually be got from MARA website, which is the Marine Area Regulatory Authority of Ireland. They're on their website. So if anyone has access to that, they can actually go in and search for new licenses and all that, get all this information and get the actual owner of the cable as well. But it's artificial intelligence, which is the driver behind all of these. These are new cables that are actually coming from Ireland, not from the UK or any of that. They're actually coming from Ireland. There's 2 more cables again, going from Ireland to the UK. The one previous was going to America. That's Ireland to the UK. There's more Ireland to the UK again, different systems. All hyperscalers, all knowing that Ireland is a place where digital communications, digital systems, and the digital economy is growing. Even though previous governments decided to put embargoes on data centers, and they say data centers are eating up the power, they're not. You can go and turn off a data center. We wouldn't be talking today, because everything we do on a laptop, everything we do on a mobile phone, everything we do on digital communications goes through a data center. It's all around the world. And data centers in Ireland carry traffic from all around the world as well. So basically, you shut all the data centers in Ireland, you create an economic disaster, right? And an awful lot of parties don't realize that. An awful lot of parties are saying, let's shut them down. They're using too much power. No, let them shut down for a day and see what happens. I'd love to see what happens. Actually, really wouldn't, but you can just imagine. Here's an example of the longest submarine cable ever deployed. It goes from Bude in the UK all the way to Marseille in France, right? Actually, it's been extended to Barcelona, but originally was to Marseille. It's the longest submarine cable in the world. It looks like as if it's only a single, but it's not. It's actually protected. There's a cable that actually goes. I'll go back. Sorry, cable actually goes across France and then across the UK, and there's two of them. It's actually connecting. It goes from France to the UK and then connects back to Bude as well. It creates a big ring. So if you have a submarine cable break here, traffic will actually switch this way. And it'll switch in milliseconds. You won't even know it switched. The only traffic that'll actually pick up a switch is voice. And even that is fairly quick. And then a voice is done over VoIP, which is the Ethernet. You can actually probably even wouldn't be able to hear it. So basically, even if it did switch, you wouldn't probably know it switched. But if it was ordinary voice over TDM method, you would hear it. And that's the only communication network that actually see the switch. Another submarine cable, which is going to be the biggest one, is actually called with the Waterman project. It's actually another hyperscaler, which is actually going around the southern hemisphere. It's not even going near Europe. All right. It's actually connecting all the countries on places where all these countries here would connect through Europe before they connect to the States or connect to Asia. Right. So instead of going through that, now they're going direct. It's in planning stage at the moment, but it's actually going to be the longest submarine cable network in the world. This is taken from Telegraph. It's an example in 2019 of the internet connectivity around the world. And look, you can't even see Europe. Right? Right in the middle there is Ireland. And it's actually at the center of the data center digital economy in Europe. Right? Even though there's more data centers around here, all these companies, all here, all trust this small little nation to do all this. All right. Now, it's not using all power. There's more power being used in France, in the UK, in data center tech systems. But Ireland is seen as the center of the digital economy. All right. And we can't lose that. Right. The explosion in data and traffic happened in 2020, COVID. An example of this was there was two networks operational all around the globe. It was called the commercial and the domestic. So basically, you had the commercial network which operated from between 9 in the morning to 5 in the evening, and then when people went home, they turned on the domestic network. So stream from home, Netflix, things like this, play from home, stuff like that, right? So basically, when you're in work, you're logged on to your own network. So you're in-house, but you have to connect to where services and everything else around the globe. So you do that from your work network. You're not doing it from the domestic network. But all of a sudden, in 2020, start of COVID, I think I got the year right, the domestic network started to operate at the same time as the commercial network, because people are now working from home and they still had to connect into their own services to connect around the world, right? So now you're having an extended commercial network, which is outreaching into the domestic network, which was all of a sudden the capacity was gone, right? Perfect example is in 2020, we had, and just for one streaming service from here, which included probably one or two of the ISPs, right? We had 20 gig caching. 20 gig caching is where you actually bring in 20 gig of traffic into your own data center. So we brought it into our data center. So anyone in Ireland logging on to one of these services didn't actually log on to a submarine cable into a data center, go over to the States, pick it up, bring it back. They logged on to us, BT, and they picked it directly off us. So in other words, the latency was tiny. They picked something up fairly quickly. Now, it wasn't everything that Netflix or Google had, but all it was It was the top 100 TV programs, top 100 this, top thing, where people were actually used quite a lot of. By 2022, that moved up to 800 gig and even doubled, right? It was the amount of capacity that people were using. We had to rebuild the actual ISP network 3 times just to compensate. So we built it in it was a stable network in 2020. We had to rebuild it in 2021. We had to rebuild it again later in 2021 and then 2022 again, because basically we were now catching up with the capacity. So basically in 2020, we were ahead of the posse. By March, 19th of March, I think it was 2020, straight away that day, we became behind the posse. We basically started to catch up. And I was mad. It was absolutely mad. Right. The only way they can actually increase the capacity is to come up with new methods. So coming up with new methods is using a flex grid. So basically, DWDM, which is dense wave division multiplexing, allowed for up to 120 channels, right? But it was a fixed grid system, right? So basically, you had up to 0.1 of a nanometer, which is 12.5 gig spacing between channels. Now, the thing about it is that is actually on a very short haul DWDM system, because 12.5 gig channels, or 12.5 gig channel spacing, it's very, very tight. That can actually cause four-wave mixing, which can cause non-linear issues on your actual signaling itself, right? When it actually came to using FlexGrid allowed for the expansion of that, but the problem was with FlexGrid is it didn't use up as many channels. But FlexGrid is better used on multiple fibers than it is on shorter number of fibers. So if you have 4 fibers in your submarine network, you'd more use the fixed grid rather than the flex grid, because the flex grid, even though had bigger capacity of different types of channels, it also had the actual gigahertz spacing was between 50 and 75 gigahertz, right? Which is between 0.8 and 0.4 nanometers per each channel, right? But the problem with all of this was you had a limit, and it's called a Shannon limit, right? And Shannon limit is related to how much capacity you can put on an optical system without the signal to noise ratio compromising the signal itself and creating noise, right? So they also came up on 10, 15 years ago with coherent technology, where they could actually, what they did was they picked the radio network and they used the multiplexing techniques which they use in radio as in horizontal and vertical. And in each horizontal phase, they actually allowed signals, and on the vertical phase, different signals. Therefore, instead of having just one light source coming in of one electrical signal, which is the face of the light source, now you have the electrical and the magnetic side, each phase itself carrying up to 4 or even 8 data points, which allowed for an awful lot more signal, which allowed for the like 400 gig capacity. With normal signal on-off keying, you could probably only get 10 gig. But by using QPSK, PAM4, 16 QAM, which all come from radio multiplexing techniques, allowed for the increase of the actual capacity in channel.
Okay, Derek, you got a couple of minutes left, maybe. So.
Okay. By increasing the actual spectrum in submarine cables, we came up with likes of multiple pumps, for instance, and multi-core fibers. Right. Multi-core fibers are actually fibers with a single core, or the cladding with multi-core in them, different types like this. Right. And then here you have an actual operational system, which is actually in Taiwan, which is actually using multi-core fibers. It's using multiples, which actually increasing the actual system itself by a huge amount of actual signal traffic. Quantum technology and artificial intelligence are also drivers behind all of this. Right. And then we come to the map again. This is the map of the submarine cable network we have today. critical or security critical systems, all these systems all can actually affect the submarine cable, right? These are all different types that actually can cause damage, things like this, right? But these are other damages. Trawl doors, anchors, recovery of old cables, and the environment can damage submarine cables. How can the governments help, and how can the military and Gardaí customs help? These are all different things, right? Then we also come to sensing. Submarine cables are also used for sensing. They're not used just for comms. They're used for different types around the globe for sensing seismic movements, things like this. This is the very first ever sensing submarine cable network in the world, and it's in Galway Bay. Different types of sensing techniques that are used today. They use frequencies. They use sensors in amps that are branching units that actually pick up movement, pick up seismic movements, can pick up vessels, things like this. So they're no longer just picking up communication signals. They're also picking up different movements in the actual submarine cable. They have them in the amplifiers, and they have them in branching units. This is another diagram of how sensing systems are being used. And then this is the frequency sensing system, where they actually use specific frequencies in the actual optical signals in the actual cable itself that actually will pick up noise, or pick up pressure, strain, tidal movement, things like this. An example, an existing submarine cable using a specific frequency and testing it over different sections of the actual cable actually came up with seismic movements on the seafloor. Then again, back to the loop cables. Again, telegraph cables being used as sensing cables. Then, yeah, just more than comms. Right. And then this is what the Irish Communication Research Group, which I manage, the group which I have, this is all the work that we're actually doing around Ireland. We're working with the Heritage Council, we're working with local communities, we're working with local county councils in trying to redevelop the old cable stations. And I'm also recovering old submarine cables, which we're preserving, and we're protecting them, and we're actually sending them to museums, and the United Nations even have a load of them as well. And then this is research which I'm actually doing in UCD on optical systems itself. Holographic cryptography, self-written waveguides, optical sensing, and waveguide for formation in optical devices. And that's it.
Thanks.
Hope you liked it.
Thanks so much, Derek. As usual, time is your worst enemy. That was fantastic.
Sorry